welcome to our presentation on the protection of drinking water through the removal of trace organics. Trace organics, what are they? Trace organics are defined as compounds that are known or suspected to be released into the aquatic environment, however, are not commonly regulated or monitored. So the three main types of these unmonitored contaminants are pharmaceuticals, pesticides, and industrial chemicals. Pharmaceuticals, such as antibiotics, antidepressants, or estrogen, are released into drinking water through household sewage or through uncontrolled drug disposal from hospitals or nursing homes. This can be a result of a backlog or a build-up of out-of-date medication that hospitals tend to just kind of flush down the toilet to kind of get rid of them. Pesticides, specific example is atrazine. These contaminate drinking water through drain flow and through agriculture. So when pesticides are used on fields, they obviously get absorbed into the soil, and then it can get into the water through that way. Industrial chemicals such as petroleum products, phenols or ketones, this occurs through in industry, so the wrongful disposal of waste from factories. These tend to be used a big waste pipe that would flow directly into a stream or a river, which would be direct contamination. What are the issues with pharmaceuticals being in water? The effects on humans are marginal, as typically the concentration of pharmaceuticals in drinking water is very, very small. However, vulnerable people may be more susceptible to any effects through that. However, it does not help the battle against antibiotic resistance, because you don't want to be unknowingly kind of ingesting antibiotics, building up a resistance when there's, it would be a marginal resistance, but it's not great that it's there still. The effects on fish and wildlife, however, are a lot more significant. A specific example would be how estrogen can affect male fish. So if male fish ingest estrogen, it can have a feminizing effect on them, making them have more female-like male fish. This would affect breeding patterns. There'd be less males to reproduce, etc., which would affect the whole dynamic of the ecosystem. The issues with pesticides being in water, again, is similar to pharmaceuticals. The concentration of pesticides are not large enough to cause any side effects. If they would, it would be nausea or convulsions. However, they are typically associated with the long-term chronic illnesses, again, due to the small concentration. However, in 2003, there was actually a ban on atrazine use in Europe, as studies showed that it was associated with low fetal weight. So obviously, if pregnant women were to drink water containing atrazine, it would affect the fetus. Studies have shown that it's similar to how estrogen affects fish. Atrazine can make male frogs develop female organs, even to the extent that they can produce reproductive eggs. So again, the ecosystem will be damaged. You can see in this diagram how it shows that the largest effect is through runoff and erosion. So this is through agriculture, the pesticides running off into the rivers, etc. And this is where you see that it affects the frogs, because frogs live on the surface level, and it has a very large effect on that. How can trace organics be identified in drinking water? Gas chromatography, mass spectrometry is used to detect trace organics, as it can detect parts per trillion concentration. So this obviously would be good when you're trying to identify trace organics in like a large amount of water, like mass analyzing, that kind of thing. However, in recent years, liquid chromatography tandem mass spectrometry gives a more sensitive analysis of the trace organics, so it would be a more kind of effective way rather than the GCMS. However, even better than LCTMS would be online solid phase extraction, as this reduces the time taken in sample preparation that you would get with the liquid chromatography, and thus increasing productivity.
Gas chromatography in tandem with mass spec, or GCMS for short. Now, water samples would be injected onto the inlet port, which in turn would be vaporized, and the hot inlets to form a gas. Now this gas would be carried by the mobile phase, which would be an inert gas such as helium or potentially nitrogen, and the sample would be carried through the column. Now, different compounds or substances, in this case trace organics in water, would interact differently with the stationary phase, which is non-polar usually, such as silica or alumina. In the column, this would lead to separation from the different interactions, and the separated compounds will leave the column and enter the detector, in this case the mass spectrometer, at different times and different rates. So something that's far more polar will be carried by the mobile phase and interact with the stationary phase far less than something that's far more non-polar. And as a result, you can identify the compounds that are present from looking at the retention times as well as the peaks in the mass spec. Secondly, we have the LCMS, which is liquid chromatography in tandem with mass spec. It works very similar to gas chromatography, in which that the sample would be carried through the column in the solvent, obviously be a polar solvent and a non-polar stationary phase. Now, changing the solvent as well could lead to different retention times, and as the substances and compounds within the column would move at different rates depending upon the solvent used. And obviously, through that, a detector, in this case, another, again, a mass spec, would be used to identify the compounds as well as the retention times, depending upon the solvent used. Now, the difference in application between LCMS and GCMS is mainly in the volatility of the trace organics that you'd be identifying. Now, GCMS is unable to identify non-volatile trace organics that are present in water, whereas the liquid chromatography with mass spec is able to do so. And being able to identify non-volatile trace organics is very important, as they actually make up a bulk of the organics that are present in water. Obviously, if you have a very large number of contaminants, it may be rather difficult to identify every single one present. And as a result, there are continued methods to try and identify best possible ways to identify and remove trace organics from water, especially those that are non-volatile, as they're far more difficult to identify those that are present, as well as separate them fully and get a better understanding of what is present. Finally, we have solid phase extraction. Now, first, your sample would be conditioned. First, your polymer will be conditioned through a conditioning solvent, which will be passed through. You will then introduce your sample, and within that, the polymer will isolate the compounds and trace organics present in your sample. Then you have a washing solvent, which will wash away any impurities, and then the analyte itself is then collected during the elution step. Now, solid phase extraction is actually very versatile, as not only can it be used for removing trace organics from water, but can also allow for the enhancing of concentrations used for analytes in, say for example, liquid chromatography mass spec. Now, solid phase extraction is far faster and cheaper, and therefore more cost effective than other examples such as liquid extraction. It's very easy to use, and specific polymer solid phase extractions don't necessarily require any conditioning, saving both solvent and time. So finally, what will the benefits we'll have? Well, clearly, removing trace organics and contaminants from water is a good thing. Having cleaner, fresher water for humans to drink will lead to less likely to have any potential illnesses later on in life, especially those who are vulnerable, such as women during pregnancy, those with any sort of chronic illnesses. As well as this, improve the quality and taste of the water, less odour, and just improve the quality for us as humans generally. But on top of this, there are growing concerns with antibiotics getting into wastewater, which obviously antibiotic resistance as well is another issue altogether. And then finally, as was mentioned previously, the effect on aquatic life that trace organics can have can be really damaging and lasting. So it's fundamental that we can remove trace organics from water, for not only for our sakes, but as well as the ecosystems that we are surrounded by. Thank you very much.